the point where we left off yesterday. Okay, so we were discussing, so we saw that the theorem of Collivagen boiled down to getting an upper bound on the mod P Selmer group of the elliptic curve. And we saw that one way of achieving the desired bound would be as follows. Okay, so we would have to find a finite set of primes S satisfying the following two conditions. One is that this so-called restricted Selmer group, where we impose the classes at all the places in this set S to be trivial, that Selmer group was actually vanishing. Okay, so we needed to find an S with this property. And then once we had that, we had this way of computing the size of the Selmer group. Okay, it became the same as the size of a certain co-kernel. Okay, so in order to achieve the desired bound, now the problem becomes the problem of producing classes here. Okay, so these are classes on which we allow ramification at the primes in this set S. And in order to get the desired estimate on the size of Selmer, now we need to know something about the images of these classes under this we call residue map. Okay, so we need to be able to produce classes which are singular, and we should be able to control what the residues are, how singular they are. Okay, so what I'm going to do today is explain Collivagen's construction of what we're going to call derived Heegner classes that will ultimately allow us to get a control on this co-kernel and thereby control the size of Selmer. Okay, so today I'm going to be telling you about this construction, Collivagen's derived classes. C sub n, there will be classes defined over K, all with coefficients in the p torsion. Okay, so let me recall the usual setup. Okay, so we start off with E over Q of conductor N. Okay, and imagine quadratic as usual. Of discriminant B different from -3, -4, and satisfying the Heegner hypothesis. Okay, so every prime dividing n splits in K. And last time we introduced the notion of a good prime, but for what we're going to say today, all we're going to need is that P is odd and that the Galois image is large. Okay, so P is an odd prime such that this Galois group is GL2S. Okay. So now the first definition today is that of what we call a Collivagen prime. Okay, so definition. Okay, so we're going to say that a prime L, which doesn't divide n the discriminant or our fixed prime P, is a Collivagen prime. If it satisfies the following two conditions. Okay, so first we want this prime L to be inert in K. And secondly, we require it to satisfy the following congruences. Okay, it's actually two conditions that we're going to put here. Okay, so we want AL to be congruent to L plus 1 and both congruent to 0 mod P. Okay, and where AL is, as usual, L plus 1 minus the number of points on the elliptic curve in the field of L elements. Okay. Okay, so I have space here. Okay, so maybe make a note. Let me make a note on the next page. Okay, so the first question to ask is, okay, do such primes exist at all? And in fact, we have a plentiful supply of them. There is actually a positive proportion of primes which are Collivagen primes. Okay, so let me put that here in this note. Okay, so let's denote, as I think we did already, denote by tau complex conjugation. And consider the following set. That will denote L sub E, consisting of all the primes not dividing N, D, or P, for which the Frobenius element is okay for this field. Okay, so we take K, we join the coordinates of the P torsion points, and that's a Galois extension over Q in particular. So we look at the Frobenius conjugacy class for that prime L. So this is clear. Okay, and we want that to be okay. So as we mentioned yesterday, the prime in the ground field only determines a Frobenius conjugacy class, really. Okay, so from now on, whenever I write such a Frobenius element, depending only on the ground field, on a prime on the ground field, we're always going to take them up to conjugacy. Okay, so here implicitly I'm picking a prime in K in that upstairs, which lies above L, and what I want to require is that this is conjugate to tau. Okay, so these two elements are conjugate to tau in this Galois. Okay, so another way of phrasing this is by asking that this conjugacy class, which is really what it is the same as the conjugacy class of complex conjugation. Okay, so that would be the precise way to write that, but I don't want to have to write every time conjugacy class. Okay, so we're going to take this convention that by this tilde, I'll denote this is conjugate to that, and we will understand this conjugacy class as being an element defined at two conjugation. Okay, that will simplify the writing in much of what's going to appear later. Okay, so let's look at this set, which by Chebotarev, we know that it has positive density. So in particular, it's an infinite set of primes. And let's check quickly that any prime in this set is actually one satisfying these conditions. Okay, it's going to be a Collivagen prime. Okay, and therefore we have an infinite supply of Collivagen primes. Okay, so then okay, so this set is certainly infinite by Chebotarev. And every element in this set is a Collivagen prime. Okay, so we need to check that it's inert and the two congruences. So let's check it's inert. Okay, so for that we need to look at this Frobenius element, and Okay, so for that, we know how Frobenius behave with respect to change of fields. Okay, so that's going to be conjugate to looking at this one over the larger field. And restricting that to K. Okay, but by our definition of L, this is just conjugate to tau, so we get tau, which has order 2. Okay, and therefore the inertial degree of L is 2, so that means L is inert. Okay, so that checks the first condition, and the second one will be an easy consequence of once more the Eisler-Shimura congruent relation. Okay, so by the Eisler-Shimura congruent relation, okay, on the one hand, we know what is the characteristic polynomial of Frobenius acting on the p torsion of the elliptic curve. Okay, so we know that characteristic polynomial of this element, I can write this. Sorry. Okay, so this is the Frobenius element, and this acting on the p torsion. We know that this has characteristic polynomial with, well, we know the trace is AL, the determinant is L because it's a cyclotomic character. Okay, so this is now a polynomial in f p of x. Okay, we're looking at the p torsion, and on the other hand, that will be the same as the characteristic polynomial of complex conjugation because these two guys are conjugate by definition. Okay, but we also know what that is. Okay, so while the characteristic polynomial of tau acting on the p torsion is x squared minus 1. Okay, also build a polynomial here. Okay, and that gives us the two congruences. Okay, so we get AL is congruent to 0 mod p, and L is congruent to -1, or equivalently, L plus 1 is congruent to 0. Okay. All right, so this in particular, as I said, guarantees that there are infinitely many Collivagen primes. But perhaps more important than that, for what's going to come next, is that this fact that whenever we impose this, so any prime in this set LE is going to be a Collivagen prime. Okay, so later on, it will be important to choose such Collivagen primes appropriately, and the way we're going to check that we are indeed getting Collivagen primes is by checking that they belong to this set. Okay. So, any questions so far?
No questions. Please carry on.
Okay. Okay. Thank you. All right. So now we can make the following definition. Okay. So now we introduce somehow the magic in Collivagen's argument, which is the idea of introducing this what we now call Collivagen's derivative operators. Okay, it's a really ingenious idea. Okay, so let's take L to be a prime in this set L sub E. Okay, so we just check any such prime is a Collivagen prime. So in particular, it's inert. Okay, so and therefore, okay, so we have. Okay, that's because L is inert in K. The Galois group that I'll denote it Yes. Okay. So yeah, someone is asking why it's inert in K. So this just follows from. So to be inert, it means that it's a prime unramified in K. So that's guaranteed by staying away from the discriminant. And then we need to check that the inertial degree is 2. Okay, and one way of computing the inertial degree is computing the order of the associated Frobenius element. And that's what we just did. Okay, so we look at this Frobenius element, we found it's an element of order 2, and therefore it's a prime which is inert. Okay, if we found instead something of order 1, it will be telling us that it's a split prime. Okay, so this GL, I think I already introduced this notation. Or maybe not, I forgot. Okay, so this is the Galois group of the ring class field of conductor L over the one of conductor 1. And we already used that this has order L plus 1, and is in fact cyclic of order L plus 1. Okay, so let's pick a generator. So call it sigma sub L. And now we define the Collivagen derivative operator. Is the following group ring element. Okay, so just really denoted B sub L, and is the sum from I equal to 1 up to L of I, this generator raised to the ith power. Okay, so this is an element, so we view it as an element in this group ring with integer coefficients, which naturally acts on the group of points on E defined over HL. Okay, certainly GL does, and because it's an abelian group, it Z also acts. Okay, and the first proposition keep track of. Let me call it. Okay. Okay, let me call it proposition 3. Last time we had 1 and 2, I think. Okay, so let's pick now L, one of these primes, Collivagen primes, and Y sub L, the Heegner point of conductor L. Yes, so yeah, I think one reason why it has this name is because yes, formally it looks like a derivative. Okay, and the next proposition actually will give another justification for that. Okay, which I'll mention as well. So the Heegner point of conductor L. Then we have the following. Okay, so then when we look at DL, okay, we can apply this group ring element on this Heegner point. We can look at its class modulo multiples of P. And that gives us a class here. Which is the content of this proposition is that this it doesn't only land in here. Obviously it does, but it's fixed by GL. Okay, and this notation, this kind of process of looking at points mod P, we're going to do it a number of times. So I'll denote that by bracket. Okay, so whenever I write a point with brackets, we really understand that what we mean is it's class modulo multiples P. Okay, So let's prove this. Okay, so one easily checks the following relation. Okay, so okay, that if you take, so sigma L is our generator, and if you time that with this of L, you get L plus 1 minus the norm from HL down to H1. Okay, this inequality taking place in this grouping. Okay, where this norm is the element in the group ring that apply to elements takes the norm. Okay, so where this norm is okay, so what you do is you need to take all the conjugates. So as a group ring element, you're applying this operator, or equivalently in terms of the generator, that's the same as this sum. Okay. So this identity, it's immediate to check. One can easily do it as an exercise. Okay, but now let's take this equality and apply YL to it. Okay, so this implies that now if I take sigma L minus 1 PL applied to YL, okay, so we're going to get L plus 1 times YL minus the norm HL down to H1 of the point YL. Okay, but now you might remember an expression for this that we saw in the first proposition, that was the norm relations. And what we're going to get is AL times the point of conductor 1. Okay, so by the norm relations, this is L plus 1 YL minus AL times Y sub 1. Okay, so this by the norm relations. Okay, but now we took a prime in this set L sub P, which all consist of Collivagen primes. So L plus 1 and AL are both divisible by P. Okay, so this element here belongs to P times EH sub L. Okay, so what this inclusion is telling us is that the class of this guy, modulo P, is being fixed by sigma L, okay, because sigma L minus 1 kills it. But since sigma L is a generator, that implies it's fixed by all the elements in GL. Okay, so that concludes the proof. Okay, and the comment I wanted to make regarding the why is this called a derivative operator. Another way to see that is, okay, so as we just seen, okay, this when we apply this L plus 1 minus norm, we get something that becomes divisible by P, and on which sigma L is acting trivially. Okay, so in other words, sigma L is the same as 1. So applying this DL is the same as taking that expression and dividing by sigma L minus 1. Okay, so it's a formal operation that resembles taking an actual derivative. Okay. All right, so now, so this is for a single prime, but now what we're going to do is going to take square free products of such Collivagen primes. Okay, so let me introduce the notation for that. Okay, so okay, so let M sub P denote the set of all square free products of Collivagen primes. My guess is no, but I'm not entirely sure. My understanding of Stein's method is that it's kind of the base class of Collivagen's argument. So, but I'm not entirely sure. Yeah, I can only have a guess. Okay. Okay, so N sub P is the set of all square-free products of Collivagen primes, or rather primes in this set LE, and with a convention here that we allow the empty product. Okay, so by convention, one is an element here. Okay, and now for every such integer in this set, let's set G sub n. Okay, so notation will be consistent with the previous one. Okay, so this will be the Galois group of Hn over H1. Okay, and because we're taking square-free products, this Galois group will actually decompose into the product of the GLs for the different primes that divide n. Okay, so this will be the direct product of the GLs over all the primes dividing n. Okay, where GL is yes, before this one. Okay, and also we're going to define a corresponding Collivagen derivative operator with for a group ring for this group, okay, which quite naturally will just be defined to be the product of these TLs. Okay, and now this is in this group ring, and this is the corresponding Collivagen's derivative operator. Okay, and again, we need to specify what it is for n equal to 1. Okay, so the convention in that case to be for completeness. Okay, so we declare G1 to be Z in that case, and we take B1 to be just 1, also by convention. Okay, so then the same proof that we've just given, now you can apply it to this Dn acting on the Heegner point of conductor n. Okay, and the exact same argument shows that when you look at things mod p, you then become Gn invariant. Okay, so then the same proof as proposition 3. Shows the following, that if I apply Tn to the Heegner point of conductor n, I look at its class modulo multiples of p, we get a point which is fixed by this Gn. Okay, we're here as before, Yn is the Heegner point of conductor n. Okay, so that's good. As we're going to see in a second, that's going to be crucial in being able to produce classes defined over K. Okay, so we have this, our starting point from the Heegner point construction. Our classes are these Heegner points, which are defined over higher and higher extensions of K as we increase the conductor. Okay, but on the other hand, to be able to bound the Selma group using the method we outlined last time, we need to produce a supply of classes, all defined over K. Okay, so the way Collivagen is going to achieve that is by first taking these Heegner classes of higher conductor, but then by applying these derivative operators, he's going to be able to massage them so that they become Galois invariants, and therefore they will descend to classes defined over K. Okay, so we can almost do that now, but we just need one additional step, because taking Gn invariants is going to descend from Hn down to H1. Okay, so to go to K, we just need to do some further averaging to make things descend to K. Okay, so we have this, and therefore we now do the following averaging. Okay, so if I let script S be a system of representatives, for, okay, so I'm going to use this notation, calligraphic Gn over Gn. Okay, so I'm gonna write a diagram in a second. Then we get this point, P sub n, which is defined to be the sum over all these representatives as Dn Yn. Now this will satisfy the Pn bracket, so its class modulo P is now invariant under not only Gn, but then after taking this averaging, it will become invariant over the larger group. Okay, so it's in EHN of P fixed by Gn. Okay, so let me write this picture, because these Galois groups will appear over and over. Okay, so the little picture we have is that we have this Hn, this H1, and this K. Okay, the Galois group of, so this is nothing but the Hilbert class field. Okay, is the green class field of conductor 1. So its Galois group is the ideal class group of K, but we're not going to use that so much. So let me just put here, this is what we're calling Gn. And this one here is G sub n. Okay, and therefore a set of representatives for this quotient is going to be in one-to-one correspondence with the class group of K. All right, so now we have these points. We have produced these classes mod P, which are invariant under Gn. And now to produce homology classes, quite naturally, we're going to take their Kummer images. Okay, so thus we have the following picture. Okay, so if we were just to take the Kummer images of the Heegner points themselves without further work, that would not be so good, because it would take us to classes defined over Hn. Okay, but sitting inside here, there is the space which are fixed points under this Galois action. And then the Kummer map is Galois equivariant. So it will take fixed points to fixed points under Galois action. So this will, the Kummer map will take this subspace to the corresponding homology classes fixed by the same Gn. Okay, and here we have a natural inclusion. And now here is where we use our hypothesis on the prime P that we haven't used yet. It will, so we want to produce classes really defined over K. And we've already seen that whenever we have a subgroup, we can take the natural restriction map in Galois homology. So certainly there is a natural restriction map, which typically has some kernel and co-kernel. Okay, but in our case, given our hypothesis on P, this is going to be an isomorphism. Okay, so this map here is restriction to HN, and this is an isomorphism. And let me say a few words. Why is that? Okay, so this follows from the fact that we don't have any P torsion rational over Hn under our hypothesis on P. Okay. So the way, I don't go into the details of this little calculation, okay, but the H0, the kernel of this restriction map will be controlled by some H0 and the co-kernel by some H2, but both will vanish whenever this condition holds. And the reason why we have this is because of this assumption that the Galois group of the P of adjoining the P coordinates of the coordinates of V torsion is GL2FP, while on the other hand, this extension is a generalized, the Galois group of Hn over Q is a generalized dihedral group. Okay, and it just follows from the classification of subgroups of GL2FP that it doesn't have any such quotients. Okay, so that's how quickly how one checks this isomorphism. Okay, but now we have produced a class here. And now this naturally leads to defining an obvious class in this space over here. Okay, we're going to define a class Cn to be the unique class here that when we take the restriction, it maps to delta of this class. Okay, so that's Collivagen's derivative construct. Okay, so Collivagen's derivative classes. Okay, so for every n, we define Cn in H1 KEP to be the unique class such that when we restrict to Hn, this class, okay, so when we apply this isomorphism, we get delta. So the Kummer map applied to this massaging of the Heegner point of conductor. Okay, so that uniquely determines the class Cn, and all we're gonna use, all we're gonna need about it is this defining property. Okay. But we can box this. Okay, any questions? Yeah, that's right. That's right. So n sub b is as defined up here is a set of all square free products. Okay, so let me make a little note about what is the class of conductor 1. Okay, so C sub 1 is actually something that has already appeared. That will be used later. Okay, so what's the class, the Collivagen derivative class for n equal to 1? Okay, so for n equal to 1, well, this derivative operator is defined to be 1 by convention. Okay, so P1 is just taking the sum over this set of representatives, script S, of yes, what? Okay, so the need of these derivative classes is actually summarized in this item. Okay, so so we have Heegner points, one for each conductor n, and the one of conductor n is defined over this big extension H sub n. Okay, so just from the points themselves, the natural thing to do would be to take their Kummer images, but that would give us classes which are defined over this big extension of K. Okay, but in order to be able to bound Selma groups by the strategy we explained yesterday, what we need instead are classes defined over K. So Collivagen's derivative operators are going to be useful because it will be able to modify these points y sub n, so that when we look at them mod p, we land in this space fixed by the action of Galois. And since the Kummer map respects the Galois action, the Kummer image of these modified Heegner classes, modified by these Collivagen derivatives, will give us classes on this space, which is now isomorphic to this one, and therefore it will allow us to produce the classes that we need. Okay, so that's the use of Collivagen's derivative. It will allow us to, even though we have Heegner points defined over higher and higher extensions, after applying these Collivagen derivatives and looking mod p, we get classes that descend to K. Okay, and that's in general what happens for general Euler systems. Okay, so as I briefly mentioned in the first lecture, in general, the system will be a collection of classes defined over a collection of abelian extensions of the ground field, but then this process of Collivagen derivatives will allow one to produce classes all defined over the ground field, but by at the expense of changing the coefficients. Okay, so here we look at the p torsion in order to be able to achieve that. Okay, so we were looking now what is the Heegner point of conductor 1. Okay, so by definition, this is what we do. We apply these different S's to the Heegner point of conductor 1. Okay, but this set of representatives is, as we mentioned, in one-to-one correspondence with the Galois group H1 over K. Okay, so that's the same as taking the sum H1 over K, let's say sigma. Okay, but this is the norm from H1 down to K of y sub 1. And that's the point that we've seen a number of times already, this y sub K. Okay, so this is as in the statement of theorem A or A prime, all the theorems, Collivagen theorem in the first vector case. They are all the same yk. Okay, so so in particular, what we're saying is that this condition here is nothing but taking the Kummer class. So the class C sub 1 is the same as the Kummer map of y sub k modulo p. So we get that y sub k is, and now we see why this condition it's likely to be useful for us, because tells us that yk is non-zero. Sorry, yk is indivisible if and only if C1 is non-zero. Okay. Okay, because yk being indivisible is telling us that this class is non-zero, but that's the same as C1, so we get the equivalent. Okay. All right, so we're gonna see how that's gonna be useful later. Okay, but so this little note tells us in particular that this condition that we will ultimately impose guarantees that this system of classes is is non-zero. Okay. At least the class T1 is something non-trivial. Okay. So it's a remark I think I'll refer to later. Okay, so now we have this system of classes. We know that YKB indivisible guarantees that C1 is non-zero. So what we know, the next thing we want to do is study the rigidity of this system. Okay, so we have one Cn for every n, and what we would like to now be able to do is, once we know that one of these classes is non-zero, we would like to deduce the non-vanishing of more classes. Okay, and as we're going to see, the rigidity of this system of classes will allow us to see that. Okay, so let's now look at rigidity, or properties rather, maybe properties. Of these classes. Okay, so we have one for every n in this entropy. Okay, so the first thing we want to study is their behavior under the action of complex conjugation. Okay, so here's where we use, so P is still as before, it's a prime, it's a not prime with Galois group GL2FP. Okay, so since P is odd, the action of complex conjugation is going to decompose our space of interest. Okay, decomposes. Okay, into the plus and minus eigenspaces. And what we're going to see is that each of these CNs land in one of these eigenspaces, but the eigenspace in which they live will actually alternate every time we add a prime to the conductor. Okay, so this is proposition 4, I guess. Okay, so let n be one of these integers for which we have defined these classes, and epsilon to be, as it was in lecture 1, the opposite to the sign in the functional equation. Okay, so such that LES is minus epsilon LE2 minus S. Okay, so then it turns out that the class C sub n belongs to the following tau eigenspace. Where epsilon n is epsilon times minus 1 to the number of primes that divide it. Okay. Okay, so and since, so next time we're going to be using, well, this will be used next time, so let me now make this a necessary remark, but let me do it nonetheless. Okay, so if we take different Collivagen primes, okay, so we have the class C1, which is the Heegner point y sub k, as we just saw. This belongs to the epsilon eigenspace. Then the class for CL1 will be the minus epsilon. Then CL1, L2, and the epsilon, etc. Okay, just to be very clear about this. Okay, and the proof is just a computation. So this I'm just gonna, yeah, basically, yeah, say very little. Okay, so this is just a direct computation. Okay, but let me tell you what the key point is. Okay, so the key point is the following two facts. So one is that, so this class Cn has been constructed from starting from the Heegner point of conductor n, and this one we know how it behaves with respect to tau. Okay, and it's essentially a tau eigenvector with eigenvector epsilon. Okay, so but not quite. Okay, so really what one have is this times sigma yn plus a torsion point for some sigma in Gn. Okay, the Galois group of Hn over K. So that's one thing one uses. And the second is that this extension of Hn over Q is a generalized dihedral group, as we already mentioned. Okay, so and the relation the tau sigma is sigma inverse tau for all sigma in Gn. Okay, and from this you can almost see how the calculation is going to go, because every time you add a new prime to the conductor n, you're going to be applying one of these DLs. And when you look at the action of tau, at some point you will need to swap the DL with tau. And every time you do this change, this swapping, you need to use this relation. And every time you're going to be alternating the sign due to that. Okay, so there is nothing more conceptual than that in the proof. One just uses the definition and computes quite straightforwardly. Okay, so okay, but that's going to be something we're going to be using. Okay, so that's one property of these classes. And the second one, which is also very important, is, and this we're going to put in detail, is about the control on the ramification. Okay, so remember that to bound the size of Selmer, we need to estimate that residue map. Okay, so we need to produce classes which are allowed to have singularities at these places in S, and we should have some way of controlling their singularities there. Okay, and this proposition is what effectively will allow us to do that. Okay, so let's take n, one of these integers, different from 1, the case n equal to 1 is just the y sub k. Okay, so then we know that these classes, we want to show that, well, they will follow easily. Okay, they are not going to be quite Selmer classes. They will be singular at some set of prime sets. And the set of prime S, quite naturally, is going to be, you would probably guess, the set of primes that divide n. Okay, so where S is a set of primes that divide the conductor n. And moreover, and this is the key of this proposition. Okay, so writing n as L times m with L in L sub e, and since L is inert, it's as usual LOK, call it lambda. We have the following. Okay, so remember, we're interested in controlling this residue map, this partial V. Okay, so we want to know when this is 0 or not. Okay, because we've taken a prime L that divides n. Okay, so it's a prime in our set S, and we would like to know when this is 0 or not. Okay, and this proposition tells us that we can check that if and only if, well, there's a criterion in terms of the class of conductor M. Okay, so this is going to be non-zero if and only if the class Cm, which now at the prime lambda is finite, okay, because L doesn't divide M. Sorry, I forgot to add that. It's implicit because n is a square free product, but let me add it. Okay, so this is non-zero. Okay, I can put it here. Yeah, yes, exactly. Okay, so can you write it here again? Okay, so this partial delta of Cn, this is taking place, this is non-zero as an element in H1 singular K lambda EP. Okay, and this map partial lambda is precisely the one appearing here. Okay, so we're looking at the image in this singular quotient. On the other hand, this is the restriction to the prime lambda. Okay, so this is now an equality or inequality in the image of the Kummer map as well. Okay. Okay, so is this proposition that will allow us to propagate the non-triviality of a class of conductor M to a class with further primes in the conductor. Okay, as we're going to see later. Okay, so let's prove. Let's give the proof of this. Okay, so the first part, that these classes C sub n are unramified away from the primes dividing the conductor, it follows easily from the definitions. Okay? It's not entirely trivial, but I'll just say, yeah, I won't say much about this part. Okay, so this follows. Okay, so we just prove the last claim. Okay, so now we want to decide when is this going to be 0. Okay, so the first thing we use is this Cn was expressed in terms of the Kummer image of that point P sub n. So we're going to be using the explicit description of this Kummer map with it's just a connecting homomorphism in Galois homology. So that's something that we know how to write down very completely. Okay, so by the explicit description of the Kummer map, is delta sub lambda. This is going to be non-zero if and only if the following explicit cocycle is non-zero. Sigma goes to sigma minus 1 Pn divided by P. Okay, so if and only if this is non-zero, and this is an element in H1. Now we are localizing, okay, so we are looking at this Gn and looking at the decomposition group at this lambda. So that's how I denote the decomposition group. And the coefficients here are Hn localized at the corresponding prime. Okay, so you see here this lambda and lambda n that we already encountered. So let me recall the feature we saw yesterday, which we're going to be using again now. Okay, so because now I want to write down here the Gallo groups and the decomposition groups involved. Okay, so we have Hn inside Hn, for containing Hn, K and Q. Maybe I don't need, okay, let me write it as well. Okay, and then we have L, we have lambda, all the way up here is inert. Then this is totally split. Or split completely. And here is totally ramified. Yes, so this Hn is just a completion. Okay, so whenever you have a field, a global number field and a prime, you can just complete to get a local field, and that's what this is. Okay, so this is the completion, and then that will be okay. So now I'm going to write the Gallo groups. Okay, so this is the Gallo group here is what we are denoting Gn. Now sitting inside here we have the decomposition group Gn lambda, and now because of the behavior of this prime, okay, so this prime is over here we are totally split, so the decomposition group is the same as the one over here, and now over here is totally ramified, so this decomposition group is going to be the same as this Gallo group. Okay, so this is the same as the Gallo group of Hn over Hn. Okay, but now because n is a square free product of primes, this is the same as the Gallo group of HL over H1, which is what we are denoting GL, which is cyclic. Okay, so generated by sigma L. Okay, so we're interested in deciding when this is a non-zero cocycle for this group, but now we see that this group is actually generated by sigma L. Okay, so what we need to do is evaluate, understand the image of this cocycle at this generator sigma L. Okay, so we just care about this image now. Okay, so what we find is the following. Okay, that this partial lambda Cn is non-zero if and only if this Qn, defined as sigma L minus 1, this point divided by P. Okay, so now that I'm evaluating this element sigma L. Okay. So I mean here we're using okay, so let me write. Okay, so this should be not in the kernel of the reduction map modulo lambda n. Okay, so when we look at the residue field of this Hn at lambda n, we get the residue field that we already saw yesterday, is the field with the L square element. Okay, so I did a little jump here. The only thing I'm using in going from here to here, oops, is that, so we want to evaluate this this cocycle at sigma L, and that will determine whether it's trivial or not. But so that will be whether it's trivial, where it belongs here. But in order to check the triviality of this cocycle, one uses the fact that to pass to this reduction, we just use the fact that the kernel of reduction, because we're looking at this lambda n, which lies above this prime L, which is different from P. The kernel of the reduction map is a pro-L group, or different from P. So this reduction map is going to be an injection, and to check non-triviality will suffice to check it on the spatial fiber. Okay, so that's what we are using in this equivalence. Okay, but now this is going to be convenient for us because we already understood we have this congruent relation that we proved yesterday that will be now aiding us to determine when this map is in the kernel, when this point is in the kernel or not of reduction. Okay, but now we can compute and we will easily get what we need. Okay, so remember Pn was defined as this sum over the S's in this script S, S dn yn. But now by definition, this dn was dl times, I can write it like this. And therefore now if I apply, okay, so now Qn. So now what we need to do is we're going to take this guy and apply sigma L minus 1. But we had that relation involving sigma L minus 1. Okay, so now we can use that relation that I left as an exercise. Okay, so I will give us, this is the same as the sum of S Pm, and now L plus 1 over P Ym, sorry, Yn, minus AL over P Ym. Okay, so here I use two things, right? I use first this relation to now replace that by a norm, and then I use the norm relation to replace the Yn by AL times Y sub n. Okay, so this by the norm relations. Okay, but now we know how, so the congruent relation was telling us, okay, we're looking now at the reduction. Okay, so now we look at congruences modulo lambda n, and the congruent relation was telling us that this is congruent to the following. Okay, so L plus 1, and then there was that Frobenius element, lambda m, then minus AL divided by P, and then what remains is the sum SDM YM. Let me move that to the left. Okay, so this is a congruence mod lambda n. and this is running over this S. Okay, but now this term that we have on the right is nothing but the point P sub m. Okay, so this is P sub m. Okay, and this is by the congruent relation. And now we're almost done. The only thing that remains to use is the proposition we proved earlier about the behavior of these classes under complex conjugation. Okay, and the fact that by definition these guys will be conjugate to complex conjugation. Okay, so we find is that the reduction of this Q sub n okay, because of these congruents is the same as the reduction modulo lambda sub m of this other class, or this other point rather. Okay, this multiple of Pm. Okay, which is the same as, okay, so now, okay, so when I move this outside, this is gonna act the way it acts, Frobenius act modulo L, which is as Frobenius at L, and that is acting as tau by our choice of these Collivagen primes. Okay, so this is gonna be L plus 1, then that sign epsilon sub m minus A sub L divided by P times the reduction lambda m of P sub m. Okay, so this is as classes here, as points on this epsilon m eigenspace. Okay. Okay, so what we are using here is just that hm over q lambda m is tau by our definition of Collivagen primes, and proposition 3 or 4. Okay, so now we're done really, because we want to know when this goes to 0. So now it's equivalent to this. So we deduce using the fact that this quantity we have here annihilates the target. Okay, so what this means, this thing over here is just telling us that L plus 1 minus AL kills the points of phi defined over FL. Okay, that's clear. And the minus eigenspace is killed by L plus 1 plus AL. Okay, so that's what this is saying. Okay, but from this we conclude that this reduction is going to be non-zero if and only if this point is being put it here. Is not divisible by P. Okay, but again, using the fact that the kernel of reduction is pro L and L is different from P, that's going to be injective on multiples of P. So that's going to be equivalent to the point itself being indivisible over the local field. And now this by definition of our classes CM, that's equivalent to CM lambda being non-zero. Okay. And before we already showed this, okay, so we have this equivalent to this not being in the kernel, and this not being in the kernel equivalent to this. Okay, so that gives us proposition 5. Okay, which is probably the one that took us the most work to prove, but it's also one of the more important ones that we will be using. Okay, so are there any questions? Okay, so we're almost done. I'm almost, this is much of what I was trying to say today. So let me now make the following remarks. Okay, so this proposition we just finished proving tells us that this system of classes of Collivagen's derivative classes are what we now call, after Mason and Rubin, a Collivagen system. Okay, so proposition 5 shows that the classes form a multi-Collivagen system. Okay, so that's one thing. Okay, so in general, this process that we have explained in this particular case can be applied more generally, and starting off with an analogous system, essentially the same derivative process would produce what is now called a Collivagen system. Okay, and the second remark is, again, let's look again at the case of n equal to 1. Okay, so in particular, yes, TP of E is a p-adic model. Okay, so taking m equal to 1 in the proposition, we get the following. We get that for any L in L sub P, writing LOK equal to lambda as usual, we have that partial lambda C1 is non-zero. Okay, so this, sorry, CL if and only if C1 lambda is non-zero. Okay, that's what the proposition specializes in this case. But then by construction, this is equivalent to this point P sub 1, which we already argued is nothing by the point Y sub k in the statement of the theorems, is P indivisible, but now locally. Okay, so before we saw that if, sorry, not divisible. Okay, so if the point y sub k was indivisible globally, that was enough to guarantee that C1 was non-zero as a global class. And now if it's indivisible locally, we get now that this class is also non-zero, and in fact, it's singular there. Okay. I still have, yeah, so maybe the last remark here, which is more of an aside. Okay, so Collivagen constructed this system of classes, and we have already argued that if we assume that y sub k is indivisible, this system is non-trivial. But Collivagen conjecture that this system that he can produce is always non-trivial. Okay, so maybe the class T1 is trivial, but there should always be some n for which this C sub n is non-trivial. Okay, so if I call this, I don't know how to call it, the infinity. Okay, so Collivagen in 1991 conjecture that this system is always non-zero. Okay, and much more recently, this was actually proven by Wei Zhang under some hypothesis. So this was proved. Okay, and then other works cover other cases under my hypothesis. On the P torsion. Okay, and in fact, P at least 5 and good ordinary. Okay, so this system that Collivagen introduced in order to prove his results on BSD for curves of rank 1, actually they have a bearing on the arithmetic of elliptic curves, regardless of the rank. Okay, so one can show that this system is non-trivial, or at least it's expected to be non-trivial in all cases. Okay, so I think that's pretty much. There's a question here. Yeah, certainly. So maybe we'll hear something about this in Chanjo's lecture series, but certainly this theory of Collivagen system has been developed by Messer and Rubin and others in much more general setting than just elliptical. Certainly, the modes of abelian varieties is certainly covered. Okay, so yeah, this is all I was planning to say today. So now we have this system of classes, C sub n, and now what it remains to see is how to use this key proposition we have just shown, this proposition 5, to be able to carry out that strategy that we explained yesterday to bound the size of thermal group from above, and that will essentially conclude the proof of Collivagen theorem. So that we're going to see tomorrow. So I'll stop here.
Yeah, thank you very much, Francesc Castella. Are there any more questions, comments, remarks?
Yeah, I have a quick question. So you spoke about this mod P Euler system, the Collivagen system. So have the mod P analogs of, we know that Euler systems are rather sparse, right? You don't get too many Euler systems. But in the classical case of the known Euler systems, what can one say about the associated mod P? Is there a mod P version? What does one know about them and so on?
Yeah, so for example, an analogous situation that has been quite studied is the setting of Kato's Euler system. So in that case, one can do a similar. One can always, whenever one has a Collivagen, an Euler system, one can apply this derivative construction of Collivagen, produce a Collivagen system. So, there is a corresponding conjecture analogous to this conjecture of Collivagen in the setting of Kato's Euler system, and that can be related to some conjectures of Kurihara involving modular symbols. And again, that might be something that Chanho maybe will say something about. So certainly in the case of Kato's Euler system, there is a parallel story. For other Euler systems, I think maybe one doesn't have such a fine control on the integrality of so yeah, I think these Collivagen systems are expected to be what are called primitive under some hypotheses, but maybe there hasn't been a general conjecture formulated. It's just in specific cases like Kato's Euler system or Heegner points, one has a conjecture predicting when, under which circumstances the Collivagen system should be primitive. So this mod P collection of classes should be non-trivial, but maybe there is no general conjecture yet.
Okay, thanks.
Can I ask a question?
Yeah, sure, please.
So why does the elliptic curve doesn't have p torsion over Hn? Is it because of some ramification reasons or?
No. So this I briefly mentioned where that was coming from. So the key point is that, yeah, so why this is vanishing. So if it was non-zero, then you see that the image of the mod P Galois representation would have, so the Galois group of this extension of adjoining the p torsion to Q would have a quotient, which is, we have this Galois group of Hn over Q as a quotient. And but this Galois group is a generalized Hida group. And then one just knows what are the subgroups of GL2FP very well. And as long as P is odd, you see that it doesn't have any quotient which is of generalized Hida type.
Thank you. Okay, thank you.
Yeah, no problem.